This is a really nice question about unicycles, bicycles, and tricycles. Unicycles with one wheel, bicycles with two, and tricycles with three. So we're told that there are 7 saddles in total. Each one of the vehicles is going to have a single saddle, and therefore if I say that there are U unicycles, and there are B bicycles, and there are T tricycles, if I add all of these up, then I'm going to get 7. Let's deal with the wheels now. So if there was like 5 unicycles, there'd be 5 wheels. If there's U unicycles, it's going to be U wheels. For bikes, it's going to be 2B. If there were 4 bikes, there'd be 8 wheels for the bikes. I just multiply it by 2. And then for the tricycles, it's going to be 3T. If I add all those up, then I get 13. And we've got one other piece of information given in the question. So I've dealt with the 13 wheels, I've dealt with the 7 saddles. There are more bicycles than tricycles, so B is greater than T. There's a lot of unknowns here, and there's only actually 2 equations, but there's one other thing in that we know that U, B, and T are whole numbers. Actually, we have what is called a Diophantine equation, or set of equations. We're going to turn it into a single one. And it's possible to solve these to get a single solution, especially with this here. Now, because I have this condition, B is greater than T, I'm going to eliminate U from these equations. And I can do that by subtracting. Okay, I'm going to bring this down and subtract the left-hand sides. So I'm going to get B plus 2T, and then subtract the right-hand side. So B plus 2T must equal 6. It's basically the differences. I've got an extra B here, an extra 2T here, and I've got an extra 6 here. That's another way of thinking about it. So now this is my Diophantine equation, in fact, by itself. I guess this was simultaneous Diophantine equations at this point. I've never referred to it as that, but here we are with B plus 2T equals 6. Okay, so now we can just think about some different values, because sometimes there's other ways you can solve these sorts of equations. You can try and, if they have you could divide through and show that one is a multiple of something. For example, I could divide through by 2, B over 2 plus T is equal to 3. So actually that tells me that B has to be a multiple of 2 for this to work. But we can get away, because this is quite a small number, just trying some values out. So if B was equal to 1, and actually this is kind of comes into it, if B is equal to 1, then this T would have to be a non-integer. It can't work. All right, let's try B equal to 2. Then I'd end up with 2 plus something is 6. T would be 2 as well. Okay, that doesn't work because I know that B is greater than T. So I can actually skip 3 for similar reasons. I'm not going to get a whole number. Let's go for 4. So if B is 4, then T is going to have to equal 1 for that to work. And that must be the answer, because if B becomes 5 or 6, well, 5 won't work. 6 will mean that, oh, hold on, if maybe that will work. If I go with 6, then I'll get 0 tricycles. Do I know? I know there are some tricycles though, so I can rule out that solution, I think. So therefore, I have 4 bicycles, I have 1 tricycle, I have 7 in total. So it must be that the number of unicycles is 2. Okay, that one confused me for a minute, but I think we can make the assumption that there must be at least 1 tricycle, and therefore we can rule out the solution B equals 6. So that's quite nice. I could have got there quicker by using this idea. Like I said, it must be that B is a multiple of 2, so I just need to check 2, 4, 6. Once I go beyond 6, I get a negative. With 6, I get 0, so I ruled that one out. With 2, they were the same, so it must be this one here, which led to U being 2. Nice.